we are going to begin a unit on probability. In probability, what we are concerned with is the number of what we would say are good or successful outcomes divided by the total number of possibilities. So as a basic example, if I'm going to roll a die and I want to get a 4, there's one good possibility because there's one 4 on a die divided by how many sides are there? 6. Okay. Sometimes it's not that easy to figure out how many possible outcomes there are. So on a die, we can just count up the sides. There's 6 sides. But sometimes it takes a little bit more work to count our number of possibilities. And that's where we're going to start this, is thinking about counting possibilities. So we're going to talk about our fundamental counting principle today. Fundamental means really important, big idea, right? So fundamental counting principle says, if we have 2 events, now event in probability does not mean like party type of thing. Event means a choice to be made. Okay, so picking a shirt to wear is a choice to be made. Deciding what to eat is a choice to be made. So when we have 2 events or 2 choices to make, the fundamental counting principle says if one of those choices can be made m ways and another one can be made n ways, the total number of options we would have is m times n. And that extends to if we have even more choices to make. The number of decisions we need to make, we can just multiply the individual options all together, and that will give us our total number of options. So our first problem says police use photographs of various facial features to help witnesses identify suspects. They kind of show them different parts of the face instead of whole faces and say, does this look like his eyes? Is this the kind of nose he had? So they can try to put together what the suspect might have looked like so they can get a good composite. A particular program, it says, contains 195 hairlines, 99 eyes and eyebrows, and that's together as kind of one set, 89 noses, 105 mouths, and 74 chins and cheeks. The developer of the kit claims that it can produce billions of facial features. Is that claim correct, or are they just kind of saying, like, using the word billion to mean a lot, but it's not actually billions? So the fundamental counting principle says that we can multiply the individual options, and that will give us our total number of options. So we can multiply 195 times 99 times 89 times 105 times 74. And by multiplying all that together, that should give us the total number of possible faces that this kit could make. So calculators are going to be a good thing when we do this lesson because you don't want to multiply all that out by hand. So when I type that in, the calculator gives me an answer that says 1.3 and lots more numbers, and then at the end says E10. What does that notation mean? Times 10 to a power. E is the way calculator denotes scientific notation. So this means 1.3 times 10 to the power of 10. That E means we're doing 10, and the power is the number that follows it. Okay, so it's always a base of 10, and then the number that follows it is our power. How do I undo scientific notation to turn this into like a regular number?
Move the decimal point over to the right 10 spaces.
Move the decimal to the right 10 spaces. So I can move it once, and that'll put it behind the 3. If I need to move it 9 more times, that's going to make a lot of zeros here. So 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So I put in my commas to be able to figure out what this number is. That number is 13 billion. So the developers are not just using billion to mean a lot. It truly can make over 13 billion different faces by putting together those particular combinations. So if the suspect doesn't remember, or if the witness rather doesn't remember very well what the suspect looked like, they're probably not going to stumble upon it in this many options. So part B says, what if the suspect can clearly remember, or sorry, the witness, I keep saying it backwards. What if the witness can clearly remember the hairline and the eyes and eyebrows, but they kind of don't remember the rest? So they're like, I know the guy was bald, and I know he had a unibrow. So like I was pretty focused on that. I know that, but the rest of the face, I don't really remember very well. How many options are left?
691,530.
So how do we find that?
We just don't times by the hairlines of the eyes.
Yeah, so we're going to ignore the stuff we don't need to worry about. We don't need to worry about hairlines and eyes and eyebrows because we already know what those are. But we need the 89 noses, the 105 mouths, and the 74 chins and cheeks. And we multiply that together. And that gives us the number of options that are left. 691,530 different faces for that person to peruse and try to find the right one. Okay. So the fundamental counting principle says that we can multiply all of the choices we have to make, and that would give us the total number of possible ways that we could make those decisions. Questions on this problem? At a restaurant, you have a choice of 8 entrees, 2 salads, 12 drinks, and 6 desserts. How many different dinners can you make if you're going to get one of each type of thing for your meal? This is like why I struggle going to new restaurants. I'm horrible at making decisions. Like really, really bad. I cannot make decisions. Even deciding like what restaurants to go to, I can't do that. And then we get there and then there's a menu and I can't decide what to eat. So this question asks us then, how many decisions do we really have to make, or how many different possible meals could we put together here based on these decisions?
1,000.
So we've got 8 ways to choose our entree. That doesn't even seem like this is that big of a menu. Like what restaurant only has 8 things on their menu, right? But we've got 8 entrees, 2 salads, 12 drinks, and 6 desserts that we could choose from. So how many different ways could we put all that together and like go out to eat with this many people and everybody has a different meal? We multiply that all together. 8 times 2 times 12 times 6 gives 1,152. So I could go out to eat with 1,151 of my closest friends, and we could all have a different meal. Okay. Questions? The standard configuration for a New York license plate is 3 digits followed by 3 letters. So what I like to do is make myself some blanks to fill in. So I've got 3, and I'm going to choose digits. And then I need 3 more things, and those are going to be letters. And part A says, how many different license plates can we make if we're allowed to repeat our choices? So if the license plate, like AAA, was an okay license plate to do, if we're allowed to repeat, how many different license plates could we make? How many digits are there? Why are there 10? Because 0 is a digit as well. So we always forget about 0. So we've got 1 through 9, but we also have 0 as a digit. So there are 10 digits. And if we're allowed to repeat, I could choose any of the 10 for any of those first 3 spaces. How many letters are there? 26. And if we're allowed to repeat, I could put any of the 26 in those blanks. So we multiply that out and find that there are 17,576,000 different license plates that we could make that way, which is good because New York has a big population, so they need a lot of license plates. Part B, however, says, what if you can't repeat? So what if once you use a digit, you're not allowed to use it again, and once you use a letter, you can't use it again? We still have 3 digits to pick, and we still have 3 letters to pick. And I could still put any number in that first spot, but once I put a number there, I can't use it again. So how many different numbers could I put in the second spot? 9. And then 8, because once I've used up a number, it's no longer a possibility. What about for the letters? 26, 25, 24, because once you've used up a letter, it's no longer a possibility again. So we multiply that out and see how much that's going to reduce our options. So that drops down to 11 million. So we lost a little bit more than 6 million plates by not repeating. Twos, they're both twos. How many different 7-digit phone numbers are possible if the first digit cannot be 0 or 1? So if that first number can't be 0 or 1, how many things could the first digit be? 8. How many numbers could we put in the second place in the phone number? Any of them, because it doesn't give us any restrictions on the second number. What about the third number? 10, and all the rest 10, because you're allowed to repeat numbers in a phone number. So it's just that first digit had some restrictions. This one we don't actually need to plug in the calculator because multiplying by 10s just makes zeros. So we get 8 million. This actually isn't true in terms of how many different phone numbers we can make, because there are still some problems there. Although we can't begin with a 0, because that would call the operator, or begin with a 1, because that triggers long distance, there's also some other restrictions that happen as well. Like the first 3 numbers can't be 911, right? And that's actually a possibility with what we've done here, is that we could pick 911 to be the first 3 numbers, not be a problem. Also, the first 3 digits of a phone number can't be 555. Those phone numbers don't exist. That's what Hollywood gets to use when they put a phone number into a movie, so that it won't actually be somebody's phone number. So, so this isn't exactly true, but it simplifies our calculations. All right. Questions?